Welcome you all to a new session. In this session we are going to see the Verilog codes for our sequential circuits. The Verilog codes that we have seen in the previous unit was related to the combination circuits. Now in this session we are going to look after the sequential circuits. Now sequential circuits are the circuits which are having a feedback network from output to input. Such kind of circuits we call it as sequential circuits. We have already learned about flip-flops. We have already seen latches. All these circuits are having a feedback path, means it is going to have not only input and output, it is also going to have a feedback path, means it is creating three states: past, present and future. So three states will be there for given any kind of sequential circuit device. Now if you observe this particular Verilog code, we are designing these codes for flip-flops now. Now under flip-flops we have SR flip-flop, D flip-flop, JK flip-flop and T flip-flop. And we have seen in the previous sessions also how we got, how we derived the latch, and from latch how SR flip-flop got evolved, and SR flip-flop how during the time evolution how it is converted to D flip-flop, and D how it is converted to JK, and JK how finally converted to T flip-flop, and each flip-flop got its own advantages and disadvantages. Let's not focus on how the evolution got. Let's see how we implement those flip-flops using Verilog code. Now see here, here I am declaring my SR flip-flop as a module here. I am declaring my SR flip-flop as a module, that is SR flip-flop, which is having S as input, R as one more input, and clock as input, reset, Q and Q bar. Means S stands for set and R stands for reset, that you know during the subject that we have studied in the previous. Set, reset, clock, reset, Q bar, right? So reset button is I need to completely restart my functionality of SR flip-flop. Next, my input declaration SR clock reset. My output declaration is Q bar. So this particular registers means I wanted to store my output, so I am taking a register, that is which I am declaring for both Q and as well as Q bar, that is QB, and registers of bit 0:1 means REG of 0 and REG of 1 I am declaring for SR flip-flop, and always at the rate of positive edge clock, positive edge reset, means whenever my clock is at positive edge, means whenever my clock is starting at this particular point, I am able to start my function for my flip-flop. So that's the reason it is called as positive edge clock or positive edge reset. Whenever my positive edge begins, I am going to switch on my flip-flop operation. Begin means I am starting my operation, that is SR is equal to S comma R, means what, based upon my S and R values I need to give those values as input. Now if reset is equal to 0, means if I am resetting my reset as 0, then begin case SR, means I am using a switch case here, which which input need to be considered for what kind of, means for what input I am going to get what value. Now if you see S and R value, now when 2 tick D1 is to Q, means I am taking a 2-bit value of first point, my output has to, my switch case to be considered as 1 tick B0, means I am having a 1-bit value of output 0. Next 2 tick D2 of Q, means it is giving me a 1 tick B1, means 1-bit value of value 1. Next 2 tick D3 of is to Q is going to give me 1 tick B1, means it is going to have a 1-bit value of 1. Next default begin end, means I am ending my default begin as end value. I am ending my case, this is the case which I have started here, I am ending that case here. Next I need to end my this begin also, so I am ending that one. Now else if all these operations are not done, if these cases are not done at all, what is the else case? Let's see that also. Let's observe how those values can be read. Now you see here. Now else I am taking begin Q is equal to 1 tick B0, means if Q value is 1 bit of 0 value, I am ending my process. I am ending my process and I am telling that QB should be negation of Q, means Q bar will be always in opposite to the value of Q. I am ending my module. So now for this flip-flop operation, you got 4 values, that is 0, 0, 0, 1, 1, 0 and 1, 1. Now all those 4 operations, 3 operations are declared as switch and 1 operation is declared as else operation. Now for this design I need to write a test bench. Now how the test bench looks? Now see here, this is my, where it is, this is my code basically. Now test bench I have not given, I think test bench not needed for our theory also, test bench not needed. Now let's see the D flip flop. Let's write the program for D flip flop. Now this is D flip flop program. Now you know D stands for data. D stands for data, that is data flip flop, or sometimes we call it as delay flip flop also. Similar case, whatever we have written here, the switch cases for SR flip flop, the same thing for a D flip flop also. D flip flop you got only one input line, and you also know how a D flip flop looks. Let's represent the D flip flop once. Now I will draw here. D flip flop is going to have only one input, and the same input I am going to drive here, and this is the output, this is the output, this is Q and this is Q bar, this is D, right? And for this 2 I am going to provide a clock signal. This is the D flip flop diagram. The same diagram I am implementing using Verilog code. Let us see that one. Now when you observe this code, I am declaring my module. I am declaring my module DFF, means D flip flop I am declaring. D as my input, clock as my input, reset as my resetting my total machine, Q and Q bar. Now input D I am declaring, clock and reset I am declaring, and I am declaring my outputs also, that is Q and Q bar. And I need to store my output values, so I am declaring this QB bar as registers. And I am taking a temporary register which is storing a value 0. And I wanted to start my machine, or I wanted to start my operation at D flip flop at always positive edge of the clock or positive edge of my reset. Now when begin, I am starting at begin and resetting it to initial position. I am taking my temporary value to be stored with a value D. A normal temporary value D means whatever the input which I am providing, that need to be stored in a temporary variable. Yes, temp is equal to temp, means whatever the data which I am providing, it should be arrived as the same thing at the output level. So that's the reason temp is equal to temp. Now Q is equal to temp and QB bar is equal to negation of temp, means opposite value of my temp, it is going to be provided at QB. I am ending my module and end module. So this is what the operation of D flip flop. Now after D flip flop, you know we have one more flip flop. Let's get into that one more flip flop, that is JK flip flop. So this is JK flip flop. Here similarly we are declaring the modules as J and K, JK as my input values, clock, reset, Q, Q bar, and inputs are J, K, clock and reset, output as Q and QB bar. You know that we need to store the output in a register. Why? Because these outputs are to be fed along with my current input, so that my output will be a change in the its status. So that's the reason I am making a register to store my output values, and I also telling my JK inputs to be of 1:0 length. And always it should be started positive edge of the clock and positive reset. Begin. Now JK I am giving directly values as J comma K, and I am resetting my device here. This is after resetting my device, I am starting my K statement where JK and I am declaring as now D1, D2, D3. So those values I am declaring it as first as 0, next as 1, and the last one as negation of, means whatever, if I am providing Q as 0, it should provide output as 1. If I am providing 1 as Q, it should provide the output as 0. Next I am the default begin which I am ending the case, ending it, and also after that one more point I am declaring it as Q is equal to 1 tick B0. Now QB will be always negation of Q only here, negation of Q. Now after negation of Q I am ending my module and I am giving my closing comments for my program. So this is how we are going to write the program for flip-flops. The same module can be repeated for T flip-flop also. So this is how we represent any kind of circuits under Verilog code representation. Thank you one and all.